Hello everyone and welcome back to your YouTube channel and welcome to this very interesting video. It's a very practical but very useful video. As you must be aware, some of my students, they are working on establishing or creating the full detail model of different generation unit controllers. So one of the tasks is to implement the space state representation. And some of them are dedicated for automatic voltage regulators and others are working with power system stabilizer and some of them are working with governors. So today this video is dedicated to them. It's extremely simple and basic video. And this video is dedicated for people without previous experience using DIgSILENT PowerFactory. And that is the case of those master students. They don't have any previous experience using the software. And what I want is that they are able to locate the governor models inside DIgSILENT PowerFactory, inside the global library, and they must be able to locate the models, but also to see parameters and equations. So this video is basically for somebody without PowerFactory experience. If you have PowerFactory experience, please go to other videos because this will be not so funny for all of you, okay? Well, without further details, let me start this video as usual. This presentation will be located at my ResearchGate repository. Over here, you can see the link. I highly suggest that you subscribe to ResearchGate because it's a repository for researchers and scientists. And over there, you will find slides or also reports and especially scientific papers. So I highly suggest to go there. As usual, some of my video has some technical and practical stuff. So I suggest that you go to GitHub. GitHub is the place that I locate all the MATLAB, PowerFactory and other activities, a file for other activities, okay? If you are watching this video, it's because you are in YouTube. So I highly suggest, if you like, to subscribe to the YouTube channel and also leave a comment. Finally, if you are interested to know more about what we are doing in terms of research, development, and innovation in energy systems, I invite you to subscribe and to follow my social media accounts, specifically Twitter and LinkedIn. Finally, some people ask me to provide an email address in case that you have further questions. And over here, you can see my email address. Also, there is a QR code. I update the QR code and now you can scan this and you will go to the DIgSILENT Lab website. Okay? Well, let me start this presentation today. And what is the plan? Well, the plan today is I would like to start with some motivation regarding modeling. Why do we need models and what kind of models? However, this part of the video is again dedicated to my master students that they are working with specific details of modeling, and in this case is a space state representation. Then I will show you some details how to get the governor's model data inside the global library in DIgSILENT PowerFactory. I will show you initially using some theoretical slides here, how to do that, and you can follow the steps. And then we will go inside the software, DIgSILENT PowerFactory, and we will assess the data, and from there, well, the closure of this video. Well, let's start with a short motivation. And the motivation is very simple. Inside electrical power system, we have many controllers. And those controllers, they have very specific dynamics, and they are very interesting techniques to analyze the performance of those controllers. So if you remember the previous videos, I was talking about this very simple AVR, automatic voltage regulator. If you remember the previous video, I create the state space representation, and the state space representation is basically a set of differential algebraic equations. The differential equations are based on the state vector, and inside the state vector you have the state variables. And as you must remember, there are four matrices, A, B, C, and D. And when we combine all of them, we have the dynamic behavior of the system. However, having the explicit representation of any control, that will give you the opportunity to perform some very specific analysis. For instance, in the previous video, I create the state space representation of this very simplified AVR. And during that video, I analyze the time domain response when you apply a step. And in this case, we call that in control theory a step response, and we use that step response to analyze the behavior when you have a massive change in one of the inputs and see how the system behaves. However, there are many other tools that you can use to analyze the performance of the system, and even in different domains. When I am talking about the step response, it's basically a time domain response. But you can use also some other techniques for frequency analysis. Frequency analysis, like the Bode diagram, is one of the most used elements in order to analyze the performance of the magnitude and the phase angle when you are using some signals. But there are many other techniques. For instance, if you are using MATLAB, as we did in the previous video, you can have some function that you can have some functions that they will allow you to create the map of poles and zero for the transfer function, or also the Nyquist diagram. What I want to tell you is that when you have the full representation, the detailed representation of your controller, well, you are able to perform many studies, okay? However, today the job is not related with those analysis, control theory analysis. Is basically to show you how to find the governance models inside DIgSILENT PowerFactory and how to assess them in order to identify the location of the dynamic models, but also the initial conditions and parameters, okay? Well, let me go here. What I will do now is I will show you a few slides where you can follow the steps, and then you will be able to find the governance models inside the DIgSILENT PowerFactory. And before I start, I must tell you that I am using the most recent version of DIgSILENT PowerFactory. In this case, I am using DIgSILENT PowerFactory 2023, so those slides are created using this version. If you are using an older version, or in the future, if you are using a newer version, you must understand that the slides can be changed slightly because the location of the folders, controls, and other things, they can change between versions. Well, when you are inside DIgSILENT PowerFactory, at the top you will find the toolbox, and there is a very important icon at the top left, and that is the Data Manager. When you press this icon over here, the Data Manager automatically PowerFactory open this window that is similar to the Windows Explorer. With the Windows Explorer, you are able to navigate inside your system and find files, folders, and so on. Well, it's something similar inside the DIgSILENT PowerFactory. The data manager is basically a navigator that allows you to move inside the database and find many objects or all the objects that you have in your database. But I will focus in one of those elements, and that is the global DIgSILENT library. When you open the data manager, you will identify that you are opening the database. And inside the database, there are two regions. The bottom region is dedicated for the users, and in this case, you can see this icon in blue color that represents the icon of the current user that is active. But here you have the DIgSILENT library, and this is the focus of my video today. Inside the DIgSILENT library, you will find 9 folders, and those 9 folders are designed for very specific use. One folder for dynamic models, equipment types, and so on. I will go inside the folder that is called dynamic models because I want to go into the synchronous generator power plants. Synchronous generator power plants is basically the location where our colleagues from Germany, from DIgSILENT Germany, they put the folder with all the models related with generation units. And if you go inside that synchronous generator power plants folder, you will identify several other folders, and the last one you can see over here, the name is PSSE compatible. Inside PowerFactory, there are many other models. There are models created by DIgSILENT. You can see over here the folder or IEEE. However, in this video, I am focusing on PSSE compatible because inside that folder, I have 49 different governance models. And I am interested that my students assess those 49 models creating the state space representation. Well, as you can see over here, there are 49 different objects. You can see the name, all of them starting with the letter GOV, and that is representing the name of the governor. Then there are 4 letters to say PSSE, and finally underscore and the name of the governor that you are taking in account. The first step is, if you want to see the graphic representation of the governor, is extremely simple. What you need to do is going into the name of the governor that you are interested, and then use the context menu, the right click in your mouse. What I am telling you, for instance, let me take this governor over here. This is the GOV-PSSE GAST. GAST, G-A-S-T, is the short name for the gas turbine governor. It's basically the model of the gas turbine together with the governor. So I will do right button over here, then select diagrams, and then show diagrams. When you do so, DIgSILENT PowerFactory automatically will show you the graphic object representing the whole control model. What is interesting here to show you is you will see always input like small dots in green color. As you can see, every single block there is inputs and outputs. All the inputs are in green color and all the outputs are in red color. And also what is important is in this frame that I am showing you over here, you can see that on the left-hand side are located all the inputs and for the whole model, and on the right-hand side in red color, you can see here the outputs. So what I am telling you is that navigating this diagram is very simple. The first thing that you must understand is that here you have several blocks, several arrows, and some mathematic operations. If you look this diagram, it will resemble you a classical block diagram that you can find in any control theory book. However, this is not a real transfer function. What I am telling you is that inside those blocks, you can see here in this diagram something that resembles a transfer function. For instance, here this block is basically a first order transfer function, and you can see that T1 is basically the time constant used for this first order transfer function. And this transfer function is limited between V minimum and V maximum. However, inside that block, we are not using Laplace transformation. What I am telling you is that this form using Laplace transformation, the letter S, is basically just for representation, to show you in a very simple way that you are mimicking a first order transfer function. However, if we double click that block over there, we will go to the block reference. This is the element, but I want to go inside the type. In the block reference object, in this case the element, you can see here the description. There is a state variable that is named x1. There is a parameter that is called t1. There are some limiting parameters, vmin and vmax. However, the equations are located inside the block reference, type. In other words, inside the block definition. If you click here in this small arrow, you will go inside the block definition. And when you go inside the block definition, there is a tab for equations. And inside those equations, you can see over here the beautiful equations defining the dynamic that represent a first order transfer function with limiting. As you can see over here, this is the beautiful line, the second line over here, you can see x dot. Because over here, what we are writing is that the first derivative of the state variable is equal to the input minus x, where x represents the state variable. And then divide by this number that will appear over here that is related with the time constant. What I'm telling you is that inside any block, you will have dynamic models, but those dynamic models, they are represented using a state variable. If you want to understand more about these blue color words over there, these reserved words, what you need to do is go to the user manual of DIgSILENT PowerFactory and you will find more information. Every single dynamic model requires parameters, and those parameters, they are defined inside the element DSL. The element DSL is basically a compiled version of the type. And over here you can see the list with the different names and units of the parameters, and also all of them are set here to 0. However, if you want to see the full details about the model, what you need to do, the whole model for the gas turbine, I mean, in this case, I am looking into the big picture of the whole model. What you need to do is double click here at the type. And when you double click over there, what you will see is basically that you are going into the block definition, in this case, for the whole gas turbine and governor. So when you do that, the first thing that you need to understand is that from several years ago, DIgSILENT PowerFactory is using compiled models. By default, those models are created using a DLL, a dynamic library link. However, if you select over here the option DSL, well, now you can be able to see the equations defining the initial conditions of this model. And if you go to the tab representing the equations, you will find some lines over here. You can see the blue color, the word in blue color output, and that is basically some healthy verification for the parameters to identify possible errors or mistakes. Then we have a section that is dedicated for initial conditions, and then a section for defining the parameters. The very important part here for my students is this region over here. The initial conditions are created using this command INC. INC is the short for initial conditions, and as you can see inside those parentheses, you can see x2, because in this case we are initializing the state variable number 2, and is equal, you can see an algebraic equation over there. This algebraic variable, you can see that is the mechanical power, the turbine damping, multiplied by the rotor, the speed deviation. However, you must understand those equations when you finish writing the dynamics. So this initial condition is where every single person contact me and ask me, how do I obtain the initial conditions? And to obtain the initial conditions, my dear students, you need to have the full dynamic models. It's not by magic that you get the initial condition. It's not by try and fall that you get the initial condition. The initial condition must be calculated in a proper way, other way, the model will not work. Well, here you can see the section for parameter definition. You can see for instance, this is the permanent droop using the letter R, and you can see the units per unit. Or for instance, the parameter T1, that is basically the governor time constant that is represented in the units of seconds. Well, this is the end of the theoretical part. What we are planning to do right now is going to DIgSILENT PowerFactory, and from there I will show you all of these using the real software. So let's go to DIgSILENT PowerFactory. Okay, welcome back here, and we are inside DIgSILENT PowerFactory 2023. And you can see over here, let me close this. On the top here, you will find over here the toolbox, okay? And on the top left-hand side, you will find the icon for the data manager. What I will do now is a click over here, and as you can see, DIgSILENT PowerFactory open a window, and this is the window for the data manager. And here you can see that we have the whole database, and the bottom section over here is dedicated for the user. This is the user database. In blue color, you can see the icon representing the user that is active, and inside you can see some projects and so on. It's not my interest right now going there, because I am interested on this section over here that is the global library. The global library is basically where our friends and colleagues from DIgSILENT Germany, they create those magnificent and amazing dynamic models using the DIgSILENT PowerFactory environment. And that is the place that I want my students to go and find the models, okay? Well, inside this DIgSILENT library, as I say in the previous slides, there are several folders, a total of 9, and where I am really interested to go is inside dynamic models. Inside dynamic models, you will find again 9 folders. Those 9 folders you can see over here, DSL macros, but they are now, we have model for facts. They are model for facts. Some facts are created using PSSE, but also we have some other models coming from WECC. They are HVDC also. There are some HVDC models, inverter-based generation, including the famous wind turbines model following the standard IC 61400. Now, PowerFactory is going very, very hard in using Modelica. You can see over here that inside PowerFactory already defined many basic models of components and controllers using Modelica. Also, there are some mechanical loads that you can use for motors, especially if you are interested on starting motor starting studies. But my focus will be here inside this folder called Synchronous Generator Power Plants. Because inside this folder, there are 5 folders. One of them is this beautiful PSSE compatible. PSSE compatibles are models that they are similar to the models, compatible models with the software, the other German software that is called PSSE. Well, my students, they don't care about the history, but what you need to understand is that here we have governors and turbines. What I am telling you is that this region over here, you can see the folder, and now you can follow the path. It's going into dynamic models, then going inside synchronous generator, then going inside PSSE compatible, and then you go inside governors and turbines. Where in this folder, we have 49 different models, okay? We have different models starting from some of them coming from the IEEE. For instance, here you can see this is the IEEE GO. Well, this is the IEEE GO. This is the IEEE G2. But also there are some other model coming from some manufacturers. Well, today I will do the same as I did during the presentation. I will focus in this model over here. This is the governor PSS compatible, and you can see the letters over here, GAST, because this is the model for a gas turbine and a governor. What I will do is the right click. I am using the right click, And when you are using the right click inside PowerFactory, you have something similar like Windows. I mean a context menu. And this context menu, I can use diagram, and then I can show you the diagram pressing or clicking over there, show diagram. Voila, here we are. You can see over here, this is the diagram of my gas turbine and governor, okay? You can see over here, this is the model for the gas turbine, and you can see over here, gas turbine and governor, okay? As you can see, they are block diagrams, and inside those block diagrams, again, there is not Laplace transformation. Inside those diagrams, we have is basically dynamic equations. Let me show you something very simple. For instance, everyone that no control, you must remember that this block over here is a gain. And a gain is basically the output will be equal to the input multiplied by the gain. So let me double click here this basic block. And now we are inside the block reference over here. This is the element. But let me go to the very specific case, of the type. If I go to the type, you can see that the output signal is YO and the input signal is YI. And then let me go inside the equation. Voila! Over here, I can see this beautiful equation that say the output YO is equal to the gain D turp multiplied by the input YI. As you can see over here, this is beautiful because now you can see the real equation inside this block. But what is more important for me is, let's go inside this transfer function. You must know that every single transfer function inside PowerFactory is represented using differential equations. And these differential equations are created using the state variable concept. So this is the first order transfer function. You can see that the parameter is T1. You can see that the state variable is X1. Those are the names. In this case, we are limiting the first order transfer function between minimum and maximum. But then, when I go inside the type, I can see the equations. You can see over here the equations. You can see that in this case, the output is limiting the state between Vmin and Vmax. If you want to learn more about this command, please go to the DIgSILENT PowerFactory user manual. But the line that is extremely lovely is this line over here. Because you can see the starting, the left-hand side of this equation, is x dot. And x dot is the way that DIgSILENT PowerFactory understands that that is the first derivative of the state variable x. So what you can see over there is basically x dot is the first derivative of x equal to the input minus the state variable divided by T1. Of course, there are some safety verification over here, but this is basically a differential equation. So In reality, inside the DIgSILENT PowerFactory, we are using a state variable representation, we are using differential equation, but this representation over here showing the first order transfer function is to make easy people to see the representation of the block diagram and to make easy to the people to see the block representation and the whole block diagram. Finally, before I close this video, if you double click here at the name, you can see these equations of, if you finally, if you double click here, we are going to the block definition, but this is the whole AVR. I mean, this is the block definition for the whole block diagram. If you want to see the equations, you need to enable here model type DSL. Because by default, PowerFactory is using the DLL interface. That means that PowerFactory are using models that they are compiled in the way of DLL, Dynamic Link Library. So what I will do here is I will select here DSL model, and now I can see the proper equations inside the model. As I said before, this is for some safety or healthy checks, but the important part is the initial conditions. This command over here, INC, is basically telling PowerFactory the initial condition of the state variable x2 is equal to this algebraic equation that you find on the right hand side. Everybody that is related with governors must remember that this is the mechanical power, this is the damping of the turbine, and this is the speed deviation. So what I am telling you over here is that you need to define the initial conditions using proper equations. Those equations are algebraic. A typical email that I receive probably every single week is basically, how do I obtain the initial conditions? Well, that is a motive for another video, and that is a very long explanation. But to obtain those initial conditions, you must have the proper representation of your model, and that means the representation using a state variable. What I'm telling you is that those equations over there, they don't appear for magic. They don't appear for try and unfold. They appear by doing a very simple analysis using the full state model, and from there you can obtain the algebraic set of equations that you need to use for initial conditions. However, the typical situation is that people think that creating the block diagram as this and then putting here any single equation that they believe the model will work, and that is not the reality. Well, in this video, I show you how to access the library, the global library inside the DIgSILENT PowerFactory. Then I show my students where to go to find the PSS equivalent model for governors. And then I show you the way that you can see the graphic, the block diagram, the graphic representation, the block diagram. And then from there, you can go inside those models and also see the equations representing the model. So it's very, very simple for my students now to create those models using another software, to write equations using paper and pen, and to have those models ready for further analysis. Well, we reached the very sad moment because right now we need to finish this video. I hope you enjoyed this video. I hope that you learned something about governance models inside PowerFactory, the global library, and so on. And if you are happy with that, please subscribe to the YouTube channel, give a like, or if you have a question, please leave the question. And please don't ask the question, how do I obtain the initial conditions? Again, every single week I receive mails asking for that. I will prepare a video for that, but in the future, not now. Thank you very much for watching. I will see you at the next one. Bye now.